Thanks. Hi, everybody. We need to get started. So welcome to the uncertainty session of this evening. And our first talk today is going to be a online talk, and it is fiber uncertainty visualization for bivariate data with parametric and non-parametric noise models. We're going to be hearing from Tushar Atawala. Yeah, let's take it away.
Welcome to my talk on fiber uncertainty visualization for bivariate data with parametric and non-parametric noise models. Fiber surfaces generalize the concept of univariate isosurfaces to multivariate data and has applications in domains ranging from chemistry to astrophysics. As shown in this example, in the top row, the two isovalues are selected corresponding to attributes reduced gradient and electron density, and their pre-images are visualized on the right side, which represent isosurfaces that segment out bonds and atoms of the ethanediol molecule dataset. In the bottom row, instead of two isovalues, the two-dimensional traits are selected as colored polygons, and their pre-images, also known as fiber surfaces, are visualized in the respective color, which provides segmentation of atoms and bonds even at finer levels. Now, the algorithms for extracting isosurfaces and fiber surfaces assume that input data are certain, which is rarely the case in the real-world datasets. There has been multiple previous studies which analyzed uncertainty visualization of level sets with techniques ranging from spaghetti plots to uncertainty analysis of the matching cubes algorithm. And it has been shown that the non-parametric noise models provide higher accuracy of reconstruction and uncertainty quantification compared to the mean and parametric statistics. Now, the prior work in the space of uncertainty visualization of fiber surfaces is somewhat limited. This is partly because the uncertainty quantification for fiber surfaces becomes computationally more challenging due to additional number of variables in the datasets. Now, as illustrated here, in the prior studies, the fiber probabilities were derived for the uncertain bivariate data for user-specified traits, as shown on the left side. Also, the confidence intervals of fiber surfaces were derived as illustrated on the right side. However, there are two limitations of the previous approaches. First limitation is rectangular trait assumption, which limits users from selecting interesting features in the attribute space. And second limitation is the Gaussian distribution assumption, which restricts the accuracy of uncertainty quantification. And hence, in our contribution, we extend the prior work to non-rectangular traits for providing users with greater flexibility of choosing features. We also extend the work to non-parametric noise models for higher accuracy of uncertainty quantification for fiber surfaces. And we also implement the probabilistic segmentation to explore the uncertainty of fibers. Now I'll go through our approach for fiber uncertainty quantification. Now, when the data at the cell vertices for a single 2D cell is fixed or certain, essentially each cell vertex is classified as exterior or interior depending on whether it lies inside or outside the trait in the attribute space. And once each vertex is classified, the fiber surface is extracted as depicted on the bottom right image, such that it isolates exterior vertices from the interior vertices. However, when the data at a cell vertex are uncertain, we cannot deterministically classify vertex as interior or exterior, and hence we derive the probability of vertex being in the interior of a trait, which we refer to as interior probability throughout the rest of the presentation. And our solution comprises two steps. In the first step, we compute the joint probability distribution of uncertain random variables x and y, which is the product of two individual distributions for the independent noise assumption, and the joint density is depicted as the blue box on the right side. And then we study how much of that blue box overlaps with the trait T. And for that, we perform Monte Carlo integration where we draw n random samples from the joint density of x and y. And then if m samples lie in the interior of a trait as depicted in magenta, then we estimate the interior probability as m divided by n. Now, although Monte Carlo integration is easy to implement, it can be computationally expensive as the number of samples increases, as well as it can be inaccurate. And hence, we came up with the Green's theorem solution to compute interior probability in closed form. And for in the Green's theorem approach, essentially we compute the line integral of the joint density along the edges of the orange polygon, and sum the line integrals as we traverse the edges in the counterclockwise fashion. Now I won't go into the proof of how we computed the line integrals for the Green's theorem, but for that please refer to our paper. But I would like to point out that the line integral equation simplifies for the independent noise assumption because we can split the joint density as the product of two individual distributions. And we refer to this the integration table shown on the bottom for various kernels, where we plug the integral of a kernel into the line integral equation to get the closed form solution of interior probability. Now, in the case of non-parametric noise, essentially each density is the sum of multiple kernels as depicted in the center column. And now the line integral for non-parametric noise takes the similar form as the parametric noise, except that it has to go through all pairs of kernels to compute line integral, and which amounts to the quadratic time complexity. In the case of correlated noise assumption, the joint distribution cannot be split as the product of two individual distributions, and hence we capture the correlation of variables x and y by deriving a 2D histogram as well as performing 2D kernel density estimation, and then summing densities of pixels that lie in the interior of a trait T to numerically find out the integration solution for interior probability. Now I'll go through few results. In our synthetic experiment, we chose synthetic data that comprised two functions, the tangle function and sphere function, and we chose a trait such that it corresponded to the features that look like concentric circles as shown in image B. We then added bimodal noise to the ground truth data set, and then we derived mean fiber surface in C and most probable fiber surfaces in images D and E using vertex-based classification. Now, we observed that the most probable fiber surface for non-parametric assumption provided the highest accuracy of reconstruction, which is evident through the color-mapped sign distance as well as the hexagonal disk in the center, which is nicely reconstructed for non-parametric noise when compared to the other statistical models. We also have quantitative results, but for again that please refer to our paper. Now, the higher accuracy of non-parametric models comes at the cost of increased time complexity as we increase the number of histogram bins, and hence we implemented a faster GPU CUDA version, and this is possible because the computations per cell are independent of the computations in other cells. We would like to thank Jiang Chen at the Oak Ridge National Laboratory for helping us with the GPU implementation. Next, we analyzed uncertainty of the RAID-C dataset using our approach, and for that we selected a trait that corresponded to the anticyclonic vertical features. Now you can see that in the mean field fiber surface we see a rare occurrence of vertical features inside the magenta box, whereas the parametric assumption provides contrary results in image C, where a large number of vertical features are observed inside the magenta box, and the non-parametric results suggest a moderate number of vertical features inside magenta box in image D. And such inconsistency across these three models suggests high uncertainty of vertical regions inside the magenta box, which is of specific interest to oceanologists. We also demonstrate the advantage of arbitrarily shaped traits over rectangular traits, which are also evident in high resolution data, as can be seen on the top row on the right side, where carbon atoms are nicely segmented out in magenta for non-rectangular traits, and rectangular traits result in overestimation of features. Similar advantages are seen for our fiber uncertainty approach in the bottom row on the right side, where non-rectangular features again segment out the high probability regions nicely, whereas the rectangular traits result in overestimation of features. We applied our technique to asteroid impact data set as well, where the probabilistic visualizations provided higher accuracy of reconstruction compared to the mean field shown in C, as can be viewed through the inset views. And we would like to point out that the correlated noise models provide similar result to independent noise models in image E. And this is one of the reasons being, in order to reliably capture the correlation of uncertain variables, a large number of ensemble members is needed, and which are usually not available for general simulations. So to conclude, we expand previous works to non-rectangular traits and non-parametric noise models. For fiber uncertainty quantification, we provide closed form as well as numerical integration approaches for fiber uncertainty quantification. In the future, we would like to extend our work for multivariate data with more than two variables. We would like to derive closed form solutions for correlated noise models if computable. And also, we would like to explore the uncertainty in topology of fiber surfaces. So thank you. Welcome to my talk on fiber uncertainty.
Thank you so much, Tushar. That was a really nice talk. We have Slido open, and I'm also happy to take questions at the microphone if anyone has any. But I can get us started off. So I think this is really cool that we're getting better and better in representing visually these uncertainties in these really hard spaces. Do you have any indication that these better visual representations are actually helping in interpretation of the uncertainty in this data?
Yeah, that's a really nice question. So yeah, if we just look at like parametric model and look at probabilities, it doesn't really give us insight into what is the variability of fibers. But that's why I showed one of the results for the RAID-C data set, where I compared mean field, parametric and non-parametric, so three different models. And for three different models, you can see the inconsistency of results and also consistent parts for three different models. So those inconsistent parts sort of kind of give you intuition regarding where things are unstable, and perhaps can help take next steps to resolve that uncertainty.
Great, thank you so much. I think
by the way, my apologies for the overlapping subtitles. Hopefully that was that was a bit of a problem.
Well, we'll have to check out the paper to see the whole thing.
Right.
Thank you so much, Tushar, again. Really appreciate it. And I think with that, we'll probably move on to our next paper. And our next paper is evaluating the use of uncertainty visualization for imputations of data missing at random in scatter plots. And this was also an honorable mention paper, so very excited to see that. Thanks, Matt. Do you want to say anything, Matt? I'm not sure what the ceremony is supposed to be.
I don't know.
Congratulations. We'll give you a coupon.
Thanks.
Yay.
My name is Abranil. Today, I'm going to present my work done in collaboration with Shunan, Jane, Ryan, Fan, Uni, and Matt. To begin, let us focus on one part of the title of our paper: Data Missing at Random. In exploratory visual data analysis, why should we consider missing data? Well, let's start with the counterfactual. What happens when we don't consider missing data? Well, if we drop missing observations from our chart, which is what most exploratory data analysis tools today do, the chart would look something like this. The user may get a notification that there are some number of missing values. Now, if I ask you, what is the average X value of the points shown? You might guess somewhere around this value, which is the best possible estimate given the information that is available to you as an analyst at this moment. but there's plenty of missing information, which would likely lead to incorrect estimates. The other way that current EDA tools support visualization of missing values is by zero filling. In this view, you have a little bit more information, so you might think, oh, there are more observations that have the X value missing than the Y value. There also appears to be some form of negative correlation between X and Y, and you might adjust your estimate a little bit like so. But this is still insufficient information to make a calculated decision. This brings us to the second part of the paper title, imputation. There's rich literature in statistics suggesting techniques for imputation of missing data, which we can use. For instance, if we were to use mean imputation for the missing values, we get this chart. Immediately, there's much more information for the analyst, and we can maybe update our estimate for the average of X again, like so. Now, imputations are not precise. For every missing observation, an imputation process will generate an estimate with some uncertainty. The question then is, should we visualize the uncertainty? And if yes, how should we visualize it? Here we present the uncertainty of the estimated imputations using confidence intervals, a commonly used representation of uncertainty, and we get a chart that looks like this. This is the maximum possible information that we can give the analyst. However, including all possible information will no doubt increase the complexity of the visualization. But whether analysts would benefit from this additional information is unclear. For example, would analysts' estimates be improved? Would their confidence in their estimation increase? There are different ways of representing uncertainty. In this study, in addition to the control of no imputation and mean imputation, we consider 4 other representations of uncertainty: confidence intervals, probability density plots, gradient plots, and hypothetical outcome plots. Through the study, we want to evaluate whether participants are able to use this additional information when interpreting the charts. So this brings me to our research questions for this study. How do different representations affect analysts' performance in analytical tasks? And how do the representations affect their confidence in performing these tasks? And so finally, how do we evaluate analysts' performance and what do we mean by tasks? For this study, we look at how participants perform on 2 visual analytic tasks, average and trend estimation. We looked at various visualization taxonomies and identified these 2 tasks to be most likely to be impacted by the presence of missing values and imputing missing values. Another factor that we consider is missing data proportion. In this study, we considered 2 different levels of missing data proportion. The task interface that participants saw looked like this, where we provided them information regarding the proportion of missing values and asked them to enter the average into a numerical text field. We also asked them about how confident they were in their answer. The task involving trend estimation was similar. To summarize our study design, we recruited 202 participants on Prolific. They were placed in one of 6 representation conditions. Each participant completed 16 trials. They performed 2 tasks in blocks of 8 trials where the order of the blocks was randomized. And they saw 2 levels of missingness proportion, which was randomized within each block. To evaluate performance for a given representation, we use 2 metrics: bias and precision. To understand how we calculate these 2 metrics, consider that this represents the correct response, and we will have participants' responses which will be distributed around the set of possible values. We model participants' responses as a normal distribution with some mean and standard deviation. The difference between the estimated value of the mean and the correct response is the average bias in participants' responses. The standard deviation of the normal distribution indicates the precision of the responses. If standard deviation is low, participants are more precise, and vice versa. We estimate posterior probability distributions for bias and precisions for each representation condition and level of proportion using a Bayesian hierarchical regression model. The results are shown here. Because the distributions for the 2 conditions for the average estimation tasks are quite similar, we look at them collectively for the 2 levels of proportion. Here we see that all uncertainty representation conditions except hops substantially reduce bias, with the CI condition showing the greatest reduction in bias. For precision, we again look at the two levels of proportion collectively. Here we see that uncertainty conditions reduces precision when compared to the baseline, while the mean condition appears to likely neither increase or decrease precision. This suggests that there is a trade-off involved. If we care about precision, we should perhaps not present uncertainty and show only mean imputations, which will produce less biased estimates of average without decreasing precision. On the other hand, if we care about bias, it might be useful to show confidence intervals at the cost of losing some precision. We contextualize these results with the confidence measures that are provided by the participants. We argue that participants should not be overly confident in these tasks, and perhaps lesser confidence might be desirable. We notice that participants in the uncertainty representation conditions are less confident in their assessment. When it comes to trend estimation, we see that there are some differences in the estimates for the two levels of proportion, hence we analyze them separately. When the proportion of missing data is lower, that is 30%, we observe that the mean imputation condition results in a small reduction in bias when compared to the baseline. When the proportion of missing data is 50%, we see that the hops condition results in a small reduction in bias when compared to the baseline. Interestingly, the other uncertainty representations might actually increase bias. Looking at precision separately for the trend estimation task, we observe that hops increases precision compared to baseline, whereas other uncertainty representations may lead to decrease in precision. And the results are similar at 50% missing data proportion condition. Overall, we observe that for trend estimation, presenting imputed estimates using hypothetical outcome plots may somewhat reduce bias and improve precision of participants' responses, but there's more uncertainty in this result. We also observe that participants are more confident in this task compared to the mean estimation task, while their performance is somewhat worse. To summarize our results, for the average estimation task, confidence intervals are likely to lead to the least biased, but also somewhat less precise estimates. On the other hand, mean imputation is likely to lead to less biased, but also more precise estimates. For trend estimation, hypothetical outcome plots are likely going to lead to less biased estimates in certain conditions, and generally more precise estimates when compared to the baseline of not showing any imputations. With that, I would like to thank my co-authors in this paper. All the supplementary materials can be found on OSF. My name is
Okay, I'm failing because I just closed the Slido on my computer and I can't find it, or my thing. So sorry about that. That was a really nice talk, though. Do we see our speaker? Are we connected?
Hi, yeah. Can you hear me?
Hi, yes. Looks like Lace is here to save the day with a question. Oh, I think we have to turn it on.
A really great talk. I was wondering about the selection of 30 and 50% missing data, and if you could speculate about what would happen with lower levels of missing data. Those seem like pretty high amounts, and I just thought I would get your thoughts about how your work would generalize to smaller amounts of missing data.
Yeah, thanks. That's a very good question. I think in our pilot, and we mentioned this in the paper, we tried somewhat smaller data set, somewhat smaller missing data proportion of 20%. And we didn't notice that impacting the tasks a lot. I think I think that needs further exploration, because it might be a factor that the number of data points that we have, we examined 50 data points in a chart, and 20% of that, while big, may not impact the results so much. Whereas, if you have 20% missing data of a much smaller data set, that might impact the actual underlying values more significantly. So I think we didn't test that interaction in this initial study, but in our pilot for the data set that we did look at, we didn't actually find that much of a difference between the like in error and also like the potential for error in the participants, right? Because the visual measure of the estimates that the participant can make the best possible guess was very close to the actual ground truth. So in that, this is why we kind of like went with 30% and 50%.
Great. Are there any other questions? Thank you again. That was really nice.
Okay, thank you.
So I think Cindy is our next speaker. Is she here? Is Eli? So sorry. You weren't here early enough. You get go plug your stuff in. Awesome. Thank you. All right. So the next talk is dispersion versus disparity. Hiding variability can encourage stereotyping when visualizing social outcomes. And hopefully it'll be no problem hooking up. Thanks, Eli.
Good? Hello? Hello? Oh, we're good. Hi, I'm Eli Holder. I'm here presenting work that I did with Cindy Schoen. In the United States, social outcomes like health, wealth, and education can vary widely between race and gender groups. So you'll see a lot of charts like these comparing average outcomes between different groups. You'll see them from government agencies, on news sites, and even from advocacy groups. These charts are well-intentioned and straightforward and accurate, but the way that they're framed can lead to toxic conclusions and reinforce harmful stereotypes about the people being visualized. This is a framing effect related to deficit thinking, and that's what we'll unpack today. So these are the questions that we'll try to answer in this talk, and we'll start at the top with what is deficit framing. So let's take a second to think about this chart on the left. This shows average hourly wages for 4 different groups of restaurant workers. For example, Group A earns $7 an hour more than Group B. But why is that? Why do you think that Group A earns more than Group B? So a lot of people will explain these differences in terms of personal attributions about the people within each group. Good, good, okay. For example, you might say that Group A earns more because they're harder working, they have better customer service, or even that they smile more. But in reality, those differences are probably more reflective of external factors like how nice is the restaurant or how busy is the restaurant. And so deficit framing is presenting group outcomes in a way that encourages these personal attributions. It encourages blaming outcomes on the people. And this is a problem because, as we'll see, it's a very short jump from blame to stereotyping. And we'll walk through an example in more detail. But first, I want to give a quick shout out to Peter Blakely, who connected the dots between chart design and deficit thinking. And this helped me see that designs that are perfectly clear and accurate and comprehensible can still potentially be harmful in this context. So let's walk through an example of deficit framing step by step. This is the same chart, but we're changing the colors to emphasize a purple Group A versus a blue Group B. So you might look at a chart like this, and your first read is average outcomes for purple Group A are better than average outcomes for blue Group B. And that's accurate. That's a fine read. But a lot of readers will go a step further and explain the differences in terms of personal attributions. So then the takeaway becomes A has better outcomes than B because the people in Group A are somehow better than the people in Group B in some way that would produce these outcomes. And there's obviously nothing in the chart supporting a causal conclusion like that. And then the real damage is that if you believe that these outcome differences are caused by difference in personal characteristics, then you implicitly believe in a harmful stereotype about the people in group B. And that's obviously a problem. And so even though charts like these only show differences in outcomes, they can be misread as evidence for intrinsic differences between groups of people. And so how do we measure an effect like this? We gave participants on Mechanical Turk different variations of charts showing different social outcome disparities, then asked them to rate their agreement with different explanations for what caused those disparities. For example, in experiment 1, participants would see 1 of 4 charts about pay disparities for restaurant workers. And then we asked 10 questions like these two on the bottom right. As a baseline, half of the questions were external attributions, like these outcome differences are because group A works in a nicer restaurant than group B. The other half of the questions were personal attributions, like these outcome differences are because group A works harder than group B. Agreement with these personal attributions was the main measure that we were interested in, because like we said before, believing that outcomes are different because people are different implies belief in a stereotype about the people in the groups. Now, given that we can measure it, one of the first things to check for is, does this effect exist out in the wild, and how prevalent is it? And so in our last 3 experiments across all the chart types, just over half of participants attributed outcome differences to personal characteristics of the people being visualized. And so this confirms that the deficit framing effect can happen in the wild, and that charts showing social outcome disparities can be misread in toxic ways that support stereotypes. And then the next question is, why do we think this happens? What role do our design choices play in this? And so to understand how a chart might nudge somebody towards stereotyping, let's look at stereotypes in general. For example, let's consider a stereotype that people in this purple group are especially high earners. Stereotypes assume that within a group, people are more similar than they really are, and between groups, people are more different than they really are. And so this stereotype implies a distribution like this one on the right, where not only do people in the purple group earn more, their earnings are very similar, and therefore all purple people earn more than all other people. But in reality, even if average earnings for people in the purple group are higher than average earnings for everyone else, the distributions will still look something like this chart on the left. You can see that earnings are widely distributed within groups, and between groups, there's a lot of overlap. And this will generally be true for any kind of social outcome, especially when the groups are based on something as loosely defined as race. So the next question is, could certain charts create a similar misperception? Let's walk through another example, this time looking at earnings for 4 different groups. The distributions on the left should closely match something like income for different racial groups. And again, you can see that there's a lot more differences within groups than there are between groups. So if we take these distributions and plot them as something like a bar chart of average income for each group, we'd end up with a chart like this one in the middle. But when people see this bar chart, they may not imagine the distributions on the left. They may imagine something more like this. Without any indication of variability, it's easy to assume that it's not there. And just like with stereotypes, charts like these can create a false impression that people within groups are more similar than they really are, and that between groups, people are more different than they really are. On the other hand, if we show the same distribution as a jitter plot or any other chart that shows the range of outcomes within groups, it becomes very apparent that within groups, there's a lot of variation, and between groups, there's a lot of overlap. And this actually parallels real life, where the more exposure you have to people from other groups, the easier it is to see them as individuals, and the harder it is to stereotype them. And so our basic hunch was that charts that emphasize within-group variability, like the jitter plot on the left, help readers see that outcomes are very different within groups and overlap heavily between groups. And this would reduce stereotyping. On the other hand, bar charts or any other chart that hides outcome variability would increase stereotyping. We tested 6 different chart types, showing 4 different topics of social outcome disparities. The chart types varied their emphasis on outcome variability. And I'll go through each of these experiments in more detail, but across the 3 different experiments where we compared high and low variability charts, we consistently found that the charts that emphasize variability, shown here in blue, reduce stereotyping, relative to charts that hide variability, shown here in orange. In experiment 1, we compared jitter plots to bar charts for a data set about restaurant worker pay. In this case, jitter plots reduce personal attributions like group A works harder than group B, relative to bar charts by 7 points on the 100-point scale. For comparison, chart type did not have a significant effect on external attributions like group A works in a nicer restaurant than group B. And so this supports the hunch that showing variability should reduce stereotyping, but these 2 charts aren't apples to apples. So in the next experiments, we tried to isolate the effect. In experiment 2, we compared 3 different chart types, a prediction interval, another jitter plot, and a plain dot plot. In this experiment, the dot plot replaced the bar chart from experiment 1. Like the bar chart, this dot plot had no indication of within-group variability, but unlike the bar chart, it's symmetric and uses a dot as the marker, like the rest of the charts in this experiment. Then, in addition to jitter plots, we also tested prediction intervals. Like jitter plots, prediction intervals capture the wide range of individual outcomes, but unlike jitter plots, prediction intervals don't show the shape of the distribution or use individual markers that could be imagined as small anthropomorphic dot people. We also varied topic. And then for this experiment, we found that prediction intervals reduced personal attributions compared to dot plots by 7 points. Jitter plots landed somewhere in the middle, closer to prediction intervals, but not significantly different from either of the other 2 chart types. So again, in this experiment, the chart types showing outcome variability reduced stereotyping relative to charts hiding it. And then finally, for experiment 3, we wanted to see if just showing any kind of uncertainty was enough to influence personal attributions, or if it was related to seeing the overlapping ranges. And so we tested confidence intervals based on standard error around the group mean, which would show shorter bars with little overlap, versus prediction intervals based on standard deviation of the outcomes, which would show long overlapping bars for the same data set. And we found that prediction intervals reduced personal attributions by 5 points relative to confidence intervals. This suggests that just seeing uncertainty isn't enough to impact personal attribution. Instead, it's about seeing the full variability in the overlapping outcome ranges. So again, in all 3 experiments, the chart types showing variability and the long overlapping ranges reduce stereotyping relative to the charts that only show between group differences. And then the last question, given that charts can be misread as evidence supporting stereotypes and that our design choices can make a difference in this, as designers, what should we do differently? It can be tempting to try to reduce social outcomes into simple averages or easy sound bites like Group A earns more than Group B. But not only does this rob readers of important context, it can also make the disparities worse by misleading audiences towards harmful stereotypes. Social outcomes are messy, especially in the context of big issues like inequality or systemic racism. So rather than chase false simplicity, our design should lean into the messy truth. When visualizing social outcomes, the charts on the left are overly simplistic, to the point of being misleading. This can lead viewers to harmful conclusions about the people being visualized. We should do less of these. On the other hand, charts like jitter plots and prediction intervals show within-group variability and the overlap between groups. This reduces the tendency to blame differences on the people being visualized and makes it harder to misread charts as evidence for harmful stereotypes. So in visualizing social outcome disparities, especially involving people from marginalized communities, we want to do fewer charts like these on the left and more charts with more context like these on the right. And then finally, some future questions that have been on my mind. How else can visualizations impact not just the readers and the consumers, but the people being visualized? And this is especially important in the context of visualizations for marginalized communities and of marginalized communities. 2 is what other unintended side effects should be on designers' radar in general. And then 3, more generally, what do we owe our audiences? As designers, we're obligated to make charts that tell the truth, but if even straightforward, accurate charts can mislead in potentially harmful ways, does that imply we have obligations above and beyond clarity and accuracy? How responsible are we for the beliefs that people take away from our work? And I'll leave you all with that. I appreciate you, and thank you for your attention.
Thank you. That's really, really interesting work. Are there any questions from the audience? I still don't have the Slido, so if anybody sees the Slido, that would be awesome.
I'll just ask what I wrote in Slido. Given the topic of your talk, the obvious question is how much variability was there between participants and their responses to your conditions?
It ranged pretty widely across the full spectrum. So some people would consistently strongly agree with I mean, even if you take out the stuff where somebody's just like clicking the right side of the scale the whole time, some people would strongly agree, other people would strongly disagree across the spectrum.
Great, cool. I have a quick question. I work in an area that actually thinks more about very hard problems, but possibly solving solutions for from all these different communities that may or might not be represented in what we've been studying. Do you have any ideas on how people's preconceived notions of what the data might be on relate to how they might interpret this that might poorly affect?
Like how to prior beliefs?
Yeah, like not necessarily stereotypes, but something about like, oh, this is how I think the world works.
I mean, so a lot of this is based on just personal attribution biases in general, and the research on that shows that there are a lot of individual differences in terms of culture, in terms of political orientation. There's a lot of things that people kind of bring to the table that can make this better or worse. We didn't look very closely at any of the demographics that we asked for, but that is definitely a factor and something to look into, I think, more in the future.
Great. Any other questions? Okay, let's see. It looks like there's one more question I'll take on the Slido. And it's from Wes Willett, and the question is, curious about your motivation for using human figures in your illustrations in the talk. Did you consider using these kinds of human-shaped graphics in the experiments? Any speculation about the extent in which human-shaped marks might encourage, discourage stereotyping?
There's a few different studies on like anthropomorphics and what if you make take a unit chart and make them more explicitly human. And I think that there's interesting work there. It hasn't been. I don't think it's leaned strongly one way or the other. For this, it was more of an aesthetic choice, just to drive home the fact that these charts are about real people.
Cool. Thank you so much. Really appreciate your talk. Let's thank our speaker again. Our next talk is Communicating Uncertainty in Digital Humanities Research, Visualization Research, I should say, and this is by Georgia.
All right. So, hi everybody. My name is Georgia Panagiotidou. I will present to you our work on behalf of my co-authors on communicating uncertainty in digital humanities visualization research. So, data visualization is becoming a common research tool in humanistic research. Nevertheless, with all its potential to enable new research directions, it's also critiqued for its epistemological incompatibility to humanistic principles. Emerging from this debate, the field of visualization for the digital humanities has been established, adopting its own more critical design principles. Nevertheless, a topic that has been less discussed in humanistic visualization are problems of uncertainty. Bias, imprecision, and implicit errors are shown to bring skepticism, even mistrust, to humanists working with visual analytics tools. Visualizations often look too objective to be representative of the messiness that humanistic data have. Okay. And that is exactly the motivation of our research. We wanted to better understand the current humanistic data practice and coping approaches to uncertainty in order to be able to represent uncertainty in meaningful ways for humanistic inquiry. And I'll take a moment here to explain what we mean when we talk about uncertainty. We use the term to denote moments of doubt or ambiguity in the data analysis process. So such a definition includes uncertainty that derives from all stages of the analysis, from data collection up to the modeling. And I will give more examples of what I mean with this later in the talk. To answer the research question, we conducted a systematic literature review where we queried paper from visualization as well as digital humanities venues, and we filtered the papers based on some criteria that are mentioned in more depth in the paper, ending up with a corpus of 126 publications that use visualization as a core research method. We analyzed this corpus on 4 dimensions. First, we wanted to see the visualization parameters. So what was the original data source? Was it text or image? What type of abstract data did it represent? The types of visualization used, and even the software tools that were used to create it. And here in the slide, you see some of the visualizations, such as the ones we examined. I will not go into depth for the analysis of this dimension, but I refer to you to the paper for the results. The second thing we examined in our corpus were the uncertainty origins. We did that by reading through all the articles and highlighting the points where the authors discussed uncertainty in their analysis process. So here, for instance, you see a paper talking about London in the 18th century, and the authors mention 18th century spelling is notoriously inconsistent. Addresses are notoriously vague until street numbers were introduced in 1760s. So the authors are obviously expressing the issues they encountered with their process. The results of this dimensions was a taxonomy of uncertainty specifically for the digital humanities. And we found that the uncertainties to be originating from all over the analysis process, with a lot of them already coming from the source and the data. And I will mention some of these parts here. So besides missing data and imprecise, unverified data that are kind of already documented in a lot of other fields as well, we also saw that humanists encountered conflicting data. So for instance, when a historical event might have two different dates associated with it, documented by different sources. And there also were issues of human subjectivity in how the sources were ending up being data in the first place. Digitization was another major source of errors, with commonly publications talking about optical character recognition, OCR. But still there were other errors also originating from when digitizing artworks, for instance, when having artworks or films, since their color scheme might be captured differently than what it was originally. But when we talk about sources in the humanities, we talk about music, literary text, film, and these are not by default data, but they need to become data to be analyzed with visualization and other computational techniques. So this usually happens through manual classification or automated classification techniques, which, while it reduces its complexity, and while this is something that is wanted, it also brings uncertainty regarding to what kind of classification techniques are being used and what is inevitably excluded. The next thing we looked at was whether these uncertainties origins were actually represented in the visualizations that were presented in the articles. We did that by taking extracting the images from all the articles and then looking at them systematically to see what they represented an uncertainty. In fact, from the 83 articles that talked about uncertainty issues and issues with their data and things that we were talking about before, they were talking about it textually, only 20 of them actually represented it in their visualizations. So working with these 20 visualizations, we proposed a tentative grouping of how this communication actually happened. First and foremost, we saw that there was the most obvious kind of a representative, which were established methods. So for instance, here you see a map with missing data on the right, yeah, while on the left you see error bars on a time series data. But the second way that was more improvisational, and this was starting to become more interesting. So here we saw that humanists used isolated tricks or patterns to depict uncertainties or inconsistencies in their data. For instance, in this image, you see missing geolocations of folk tales in the Netherlands were mapped in the middle of the ocean so as to avoid them from being overlooked in the visualization altogether. Then there was a more experiential approach to enter uncertainty, which they gave the impression of it rather than to actually try to quantify it. For instance, to allow for more ambiguous relationship amongst documents, this software used spatial proximity. And I quote the authors mentioning that putting two items together close enough suggests some degree of connection without needing that to be spelled out specifically. And finally, we saw that there were some dedicated approaches to uncertainty that was exactly the motivation of creating that the visualization in the first place. So working with literary scholars, here you see the example of Stoffel and colleagues who created a visualization tool for directly disambiguating entities in book character networks. Finally, we looked at what other ways besides visualization did humanists mention in their articles for navigating uncertainty. And we did this in a similar methodology as we did with the origins of uncertainty. So we went through the papers and analyzed it in this way. In the paper, we talk about a taxonomy of methods that they used, of how they navigated, but I will only be mentioning 2 interesting points for the purpose of this talk. First, we saw that in some cases, the authors actually embraced uncertainty, arguing that these issues hold meaning and information in and of themselves that are meaningful to be communicated, even and retained. For instance, rather than standardizing spellings to be able, in literary analysis, to be able to make the analysis easier, the authors actually embrace the irregularities as part of the data because it might be proven useful for inquiry later on. And finally, another quite interesting way of navigating uncertainty was also the type of correcting. So the authors allowed the editing of the original data or the system already even after the deployment with the humanists. We presented our bottom-up empirical findings of how humanists experience uncertainty in their research with visualizations and how they try to address it. Our work now closes with the research agenda for uncertainty in the digital humanities. First, we propose that our taxonomy can work as open challenges for data visualization research around uncertainty. So we've seen that there's quite a few papers and research happening around missing data, but perhaps more interest can also happen for conflicting data or how to represent human subjectivity that are common uncertainties in digital humanities. Then we propose the meta design of patterns to help humanists visualize uncertainty in their own data. So as we saw that the humanists appropriated the methods that they had in order to be able to do tricks to visualize the problems in their data. So we think that we can support them by making patterns that they can actually use it in their own tools that they're actually using already without needing us all the time as visualization experts to be the ones that create the custom visualization tools. And finally, we say that our work works as a common framework from which to springboard awareness and dialogue between the 2 disciplines, between the humanities and the visualization literature research. Thank you. I'm happy to take questions.
Thank you so much. That was a really nice talk. Are there any questions? I don't see anything on the Slido, but I do have a question. I'm going to try to stay away from you. Have you looked at any humanities research that expresses visualization that is sort of pre-digital? There's been a lot, and I'm just sort of in my mind thinking that maybe there's some stuff that these folks have been, learned from for a very long time, and that maybe we could incorporate into some of our visualization techniques for this space.
Yeah, that's an interesting question, thank you. Well, the reality is that when we were looking through the papers, we didn't actually, it wasn't a criteria that it had to be a digital visualization. So there were some cases where they were actually hand-drawn or made like an Illustrator or some kind of other technique. But it's true because of the time span that we were looking at, we didn't actually capture too much of that. It would be interesting to actually see if in the past, for example, in historical visualizations, if they actually incorporated that. Thank you.
That's exactly what I was thinking of. Anything else? Okay, I think with that we will, for the sake of time, just keep moving on. So thank you again. So our final talk today is with Vaishali. She's right behind me. And we are going to be hearing about fuzzy spreadsheets and understanding and exploring uncertainties in tabular calculations. Thank you.
Hi. Hi, my name is Vaishali Dhanwa. I am a researcher at ProduFuture and a PhD student at Johannes Kepler University Linz. Today I'm going to present our joint work on fuzzy spreadsheet, understanding and exploring uncertainties in tabular calculations. So for our work, we basically take a seemingly simple spreadsheet example with uncertain information entered by the user, and we overlay it with our compact in-cell encoding we also developed a side panel to control these encodings. So why did we really think of visualizing uncertain information on a spreadsheet? Because sometimes planning isn't always a very straightforward task. For our work, we basically take, I basically use this demonstration example, which is a conference planning example, very much like this conference. So how would you go about planning a conference for a very simple example? So basically, you will take in all the incoming revenues, sum them up as total revenues, and take all the expenses, sum them up as total expenses, and then finally you can calculate a balance, which is the difference of the total revenue and the total expenses. To make an estimate for the next year, you can probably start writing the budget that you had in the previous years, and then try to average the cost for this year. But since there were worldwide events that led to a lot of uncertainty due to how many participants will appear in the offline registration, this can directly impact the cost of the venue and the catering, which will then obviously impact the cost of the balance. And you see as the balance is negative, you may go on trying projecting some other worst, average, and best case scenarios. But in all cases you see, or at least in most of the cases, you see that the balance is still negative. So you may start editing some values till you get a satisfactory result. In some cases, you may even write or create new spreadsheets altogether for the worst, average, and best case scenarios. Or you may start using other tools such as Oracle Crystal Ball, at-risk, Guesstimate, or SIP Math. But in our experience, these tools are sometimes hard to author or may even require you to leave the spreadsheet environment altogether. And as people are used to spreadsheet environment, we try to keep the spreadsheet as it is and just augment it with slight encodings. So hence our goal became to augment spreadsheet with fuzzy components such as relationship, impact, probability distribution to easily support the what-if analysis scenario for efficient reasoning. So to explain our process, I take the same conference planning example where our tool has already been loaded in. So you can simply initialize by clicking on it and choose balance, for example, and mark it as a reference cell. I chose balance because this is the cell that I want to make positive. And as I marked it as a reference cell, now all the computations will happen in reference to this cell. Next, we move on to the relationship information. So this is the information where you analyze that a cell can influence other cells and may also be influenced by other cells. And this is an important information, but it is always hidden from the user. So using our fuzzy spreadsheet technique, we basically allow you to visualize this explicit information by simply clicking on influencing the reference cell option and then choosing a degree of neighborhood. The degree 0 means you are at the cell itself. If you choose a degree of 1, it shows you the direct neighbors, such as the total expenses and the total revenue. As you can see in the in-cell encoding, we have these diamond glyphs appearing onto the spreadsheet. For this degree of 2, we see the direct neighbors of the direct neighbors, and then for 3, we see the direct neighbors of the second degree of neighborhood. And you can see right now in the in-cell encodings that the diamond glyphs are added with different colors. Now I would like to move your attention from this in-cell encoding to the side panel where you see that it acts as an active legend to visualize the information where the darker color indicates the closeness of the degree and the shape indicates whether the cell is influencing the reference cell or is being influenced by the reference cell. So now I have this network visualized. It is now important to see how these cells contribute to this reference cell. So for that, we measure the impact using our technique. And for that, we simply click on the impact in the side panel, and we see these squares appearing as in-cell encoding onto our spreadsheet. So the red cell indicate a negative impact, and the blue squares indicate the positive impact. And the intensity indicates how strong the impact is. Again, I would like to take your attention from the in-cell encoding to the side panel, where you see the percentage of this impact in exact value. So total expense, for example, has a minus 51.11% impact onto the balance. And of course, as you move on to different cells, the impact value changes because it also acts as an active legend. Now we have this impact information and the relationship information, and we move on to the uncertain part of our fuzzy spreadsheet, where we analyze the probability. So what do I mean by that? So first, we would like to have a look at the probability of an event occurring, which is specified into the column next to our cell. A probability of 1 means that event will happen for sure, and a probability of 0 means that an event won't happen at all. To view this information, we can simply enable the option again from the side panel, where you can see that the in-cell encoding have changed their size. Of course, the higher the size, it means the higher the probability of that event happening, and the smaller size means that the event is less likely to happen. Again, drawing your attention to the side panel, you can see that this information is also visible into the side panel information with the exact percentage of information. Now, after visualizing the probability, we move on to the distribution, which indicates basically the spread of a value. So we basically analyze the spread of a value by looking at the standard deviation column here. And for this case, we assume a normal distribution. Of course, you can also change your distribution values by using the drop-down menu, but for this case, we stick to the normal distribution. So when you enable the normal distribution option, you see these heat maps appearing into this in-cell encoding, where the values of these, so the range of the heat maps is between the lowest and the highest number on the spreadsheet. Again, moving to the side panel now, we see this histogram appearing, where you can hover over each bar to visualize the value in between each intervals, and then it also has this heat map added to the bottom just for an easy comparison. Now that we have all the information available of all the related cells, we can now move on to our what-if analysis. So for the what-if analysis, we can basically start by clicking on the what-if analysis option and choose a cell for which we would like to change the value. For example, in this case, the technical support, because it has a seemingly high impact and also a high probability of happening. So what if I reduce the value by 1? So the first change you will notice is this upward arrow in the balance, which means that changing the technical support has a positive impact onto the balance. And you also see these heat map has changed. So the upper distribution refers to the original distribution that we have, and the lower part refers to the new distribution. What you can additionally see into the side panel is basically the histograms that are stacked on top of each other. And you can see the original distribution and compare it to the new distribution by hovering over the same value. So as you can now see that the balance lies more in the positive range in comparison to before. As the event becomes more certain, maybe you can change the probability of the offline registration, and then also view how it impacts the balance, and make these changes until you're satisfied. Finally, you can save your changes after you're done with your evaluation by clicking on, for example, Finish and Keep New Values, and share this spreadsheet with the other organizers. Finally, we evaluated our approach by comparing fuzzy spreadsheet with the traditional spreadsheet, by measuring answer correctness, response time, and the mental effort required. We noticed that fuzzy spreadsheet helped with the answer correctness, and with the help of our in-cell encoding and compact visualization, it helped us lowering the response time and the mental effort required to solve the tasks. Finally, we recommend to stick to the familiar spreadsheet environment and augment it slightly with the in-cell encoding. You can find the demo use case example on our website, and also the paper from the QR code. Finally, I would like to thank all my co-authors, professors, and all the funding agencies. And thank you. I'm open for questions.
Thank you so much. That was a really nice talk. And interestingly enough, we had an uncertainty doc stool this year where we talked about bringing in uncertainty visualization to tools that people use. So this is very timely from that conversation. I do have a couple of questions from Slido. The first one is, what's the learning curve like for spreadsheet users to memorize and comprehend the introduced visual glyphs? What's the learning curve like for spreadsheet users to memorize and comprehend the introduced visual glyphs? How hard is it for people to understand how to use this?
So we did some tests before, and all these experiments that we did, they are available in the supplementary material. But before we started our study, we had a short presentation for each of the use cases, and the users got acquainted to the new glyphs pretty quickly, so it wasn't that hard, at least with the participants we had.
Great. We've got another question, which is in situ modeling in spreadsheets sounds like a very cool user interaction. How do you envision exploring different model outcomes or predictions as a way to understand uncertainty within spreadsheets rather than in a separate panel?
Sorry, I didn't get it.
I'm sorry. Have you thought about incorporating all of it into the main spreadsheet rather than having a separate visualization panel?
Yeah, so actually we had all the information available in the spreadsheet itself, but the problem is because of the layout, sometimes if you want to have more information, so the detailed information, it gets hard to hover over these tiny bars, and this was the reason we incorporated a side panel so that you can easily control these encoding and also have more detailed information. But the idea is that even if someone who does not have the side panels should be able to use this fuzzy spreadsheet, save it, and share it with the others and get the first overview.
Cool. Well, I've got one last question, and that is, how hard was it to get this coded up?
How hard?
To program this? Yeah.
So, took me 3 months.
That's great.
So the help is available at the Microsoft add-in website, and you can use these developer tools to program this site in using TypeScript, so it was easy for me. I don't know.
All right, well, let's thank our speaker again. And thank you all for attending this session.